Morning, everyone. This is Jim Chastain with EasyPower. Welcome to the Tuesday Refresher. And today we're going to focus on a small portion of the module we call Power Protector. The primary purpose of the series is to cover a bit more in-depth specific aspects of the tools and some of the features that may not be covered as often as needed. So again, welcome everyone. And let's start off with the poll question, as we tend to want to do. And today was specifically about the motor control centers. And I appreciate everyone participating and sharing your experience. Specifically, how many motor control centers would you see in a typical project? If you could help reply, it would give us some insight into what the audience has to deal with and modify some of the presentation accordingly. All right, let's give this another 5 seconds and see how things look. So here's how the audience voted. That's probably not too far off the norm. And then the second question is, how often do you see motor control centers that include multiple 100 horsepower motors or larger? Just turns out this is probably one of the more complicated configurations. And in fact, this session is driven by some inquiries I've had in the last 6 or 8 weeks where the engineer was dealing with the complications of exactly this type of system. So thank you very much for participating. Here's how everyone voted on this topic. Let's jump into our discussion. Okay, so the topic of series coordination we actually cover in multiple webinars, and the basic process is the same in any case, and that is when a fault occurs in my system, I want to isolate it with the protective device closest to the area of the fault and thereby prevent the rest of the system from being pulled down due to that single fault. That requires that we schedule the timing, the fault timing, trip timing of each of the protective devices in a serial fashion and slow down the ones above the bus that needs to trip first. Obviously, this complicates the situation, and I'm not going to spend a lot of time, and the process is the same every time you go through this, whether you're doing a radial system such as this, or you're doing a more complicated system involving motor control centers. So the agenda today is primarily focused on modeling alternatives for motor control centers that allow, or at least allow us to simplify what it is we're trying to consider. And so I'm going to spend less time on the specific coordination issues because they don't change. And the problem ends up being how well I can examine my system as I'm considering what these alternatives or options that I have in terms of coordination. Now, one of the things I want to amplify is the need to be specific in designating parameters which can affect both incident energy and equipment duty, because sometimes they're overlooked even in the simple systems. Then we'll talk a bit about how to locate devices with missing data, especially if they're in motor control centers. Touch on motor control center library loads, not very well discussed in our training sessions, but for some people it can be very productive as far as time savings. And then we're going to go through several examples comparing coordination using the icon representation of a motor control center, one where we have outboarded a separate load, and then compare it to a discrete motor control center coordination example. I've included a couple handouts which are available in the control box for this webinar. One is a paper that was produced by a couple of engineers from the Eaton Corporation entitled Impact of Available Fault Current Variations on Arc Flash Calculations. Very good reading, and it does have a direct bearing on the issues run into when you have a very high motor content in a motor control center. The second handout is a paper that was presented by two EasyPower engineers at an IEEE committee session. And this is discussing the arc flash instant energy calculations and ways to improve or make it less conservative in terms of the control or the current that's being used in the calculations. So both of these we're going to touch on briefly, but I make those papers available as reference material. They're not, in fact, this whole presentation is more as a reference as far as your utilization of the tools, and these are not necessarily recommendations for any project specifically. So what I'm going to be talking about is comparing a motor control center icon implementation of the tools of the system compared to a discrete bus model. The advantage of utilizing the icons is it will permit a large number of loads without consuming bus count. Sometimes that can be very important in terms of the cost of a study. The tools also allow the ability to group or lump motors into groups, and this is available actually both as a standalone motor representation on a discrete bus and in the motor control center's selection of loads. And in terms of lumping the motors, grouping the motors, these can be grouped in less than 50 horsepower and greater than 50 horsepower buckets. The ability to include the time current characteristic curves for both VFDs, motors, and loads is available, and we'll talk a bit about that in the motor control centers. And then there's also the ability to outboard or set up loads or subpanels without TCCs. One disadvantage of using the icons is the arc flash incident energy is calculated for the main bus. Now normally this is going to be a 480 volt system. If we're talking about a 240 volt motor control center, it's not necessarily a disadvantage because that's where the scope of most projects will remain or extend to. However, in a 480 volt system, the labels that are generated are generally twofold. One is for the main bucket, and as long as it's isolated from the main bus, then the labels can be generated for the main bus, which could be applied to the other buckets which represent loads on the motor control center. So the disadvantage is that there's no individual load labels and consequently no prediction for labels on a motor control center load, which may be at a distance from the motor control center. So both of those can be addressed or overcome by utilizing discrete modeling of my load system and just referring to that as a motor control center type of bus. Advocates for discrete MCC modeling will point to the advantages, and you'd be wise to take care as you construct the model, specifically how you designate what type of bus it is. And for starters, the short circuit analysis might reveal different results based upon the selection of what type of bus we're talking about. So first we're going to look at this representation, if you will, in a one-line diagram. Here I've set up a discrete motor control center bus, and I've labeled the bus under the characteristics. It has been labeled as a junction box and correctly identified as a square D model 6, which is a motor control center and a rating of 800 amps. Now the point I want to make is I'm going to isolate this particular motor control center and its buses. I'm going to go to short circuit focus. I'm going to fault all the buses that I've selected, and I don't see anything awry. There's nothing apparently out of line with the currents. But if I go to equipment duty, I see that I have some flags on a couple of devices, but there's no numbers. Now, the point here is we really want to know how the rating for any of these components compares to the actual surge current of a worst case fault. So the fact that we see some flags without numbers associated with them means that there's something fishy. Well, to that extent, and we saw this as I opened up the motor control center, there wasn't a rating on that particular bus. Well, again, I'm going to isolate on this particular part of the system. I'm going to go to the database browser and look at, so of these 5 buses that I've included, I'm going to look at a selection of some of these elements. So if I look at the buses, this shows me right away that none of the selected bus that I've designated have any bracing numbers entered, and these are what are used in comparing equipment duty. Now, I can go through and fix each one of these. For instance, if I open up this chilled water pump, this again is referenced as a small junction box, so I may not care, but in fact, the point I guess I want to make is, even if this is a 400 amp bus and it's rated for 42,000 amps, I really do want to have this in my my database, because these numbers will be used for that the equipment duty calculation. So if I kind of go, the other thing I want to look at next is going to be my protective devices. And while I'm here, let's look at cables. This tool, Database Browser, is primarily useful for looking at the system from a 5,000 foot point of view. And what I'm looking for as I scan these different types of components is anything that could be missing as far as, or incorrect as far as the data collection. And one thing I want to look at as far as the cables is if my calculations for the reactive and resistive components have been completed, and if I have any elements that have temperature compensation that I would expect to see in these columns. And here I can see I have some kind of temperature compensation going on, but not necessarily in all of them. And again, this is more of a flag. And then the final element in this system is going to be the fuse switches. And as we look at the entry point, I can see over here that we have short circuit interrupt of 300,000 amps for a couple fuses, 200,000 for another, and then zeros. And ironically, these are the 2 fuses that were highlighted in red when we first started off. Another flag or another clue to the problem is here we show a test environment for short circuit X over R value of 4.9, and for these other 2 it's 15, and yet they're all hanging on the same 480 volt bus. EasyPower automatically compensates the X over R that the manufacturer uses in the plant to test the component for our equipment duty ratio. And the fact that we don't have numbers in here that reflect what the manufacturer represented means the tool's not doing its job, or at least it's not providing the assistance that it can provide. So again, let's go back and look at, I'm going to close this report and look at one of these fuses. And what I see is I've set up the fuse with the manufacturer and the size, but when I went to short circuit, the person that did the modeling didn't click calculate. And if you've seen any of my presentations, when I'm at this point, I want to click calculate and see these numbers change. That tells me, okay, Jim, I found the part number that you gave me. There's a manufacturer's data sheet in the library, and the manufacturer tested this component with an X over R value of 4.9. The tool will then use that value and compare it against the current and the X over R value that it encounters when it runs equipment duty in this system. So now when I go back to short circuit focus, I want to just look at this section of the one line. Let's fault the components, look at equipment duty. Now just for grins, for those of you that don't know, when I go to short circuit options, again, I'm in a short circuit focus, and I look at the control tab, this equipment duty threshold that's going to turn the element red does so if it's within 10% of its equipment threshold. There are times that I may want to see or play with this number to allow me to see a broader span, and that comes into play, frankly, in motor control centers. So let's jump back into the presentation and talk about that. Okay, so the point that I want to make is that the primary focus of a short circuit analysis or short circuit study is to determine the worst case fault currents and then verify the equipment will survive in that case. Well, that requires comparing the rating that the manufacturer has presented on its data sheet with the current that we're predicting in the worst case three-phase bolted fault. And as a result, if we haven't included that rating and we haven't made the connection between our components and the device library, we're missing a big part of what are the functions of short circuit. And my point is this tools will do the heavy lifting here. We just need to be sure that we have the data loaded into the model. Okay, I'll quit beating on that one. Then the next topic is instant energy, and this goes to the two handouts that I presented. IEEE 1584 says the instant energy is proportional to the arcing current, the arcing time, the voltage, the type of enclosure, the air gap, and it's inversely proportional to the square of the distance. Well, at least that's the way I explain it. Well, it turns out sometimes the square is not exactly 2, and so this brings up what's referred to as the distance X factor. And in NFPA 70E, this is discussed as the distant X factor. When they present this is when they present the equations for the IEEE model, they show for instant energy to use this equation here, and the X in both of these locations refers to this distance X factor, which is a function of the type of bus. So just for what it's worth, E here is the instant energy that we're going to result in the case of this particular bus. The CF is referred to as calculation factor, and this is above 1000 volts. The factor is 1, and it's 1.5 for 1000 volts and below. EN is the instant energy normalized, which comes from another equation in the 4-part IEEE model. T is the arcing time, and X is the working distance. Excuse me, X is this component factor that we're talking about that varies with the type of bus and the voltage. And then the D is the working distance that we're going to be exposing people to instant energy. Now, where this takes us is the factor, the next paragraph or the next table in IEEE 1584 and in FPA 70E that explains what this exponent factor X equals when based upon the voltage or the type of equipment that we're exposing it to. So below 1000 volts in open air and for cables, the X factor is 2, so it's squared. But for switchgear, motor control centers, and panels, it's a different value. And if you kind of factor all this together and multiply out the difference, what this means is in an open air setting where the distance factor is X, then if we move the working distance from 18 inches to 36 inches, we have a 75% decrease in the instant energy. In the case of switchgear, that same movement of working distance, we get a reduction of 66%. And in motor control centers and panels, the reduction is 68%. And this can be significant. Again, it's necessary to convey the correct type of panel that we're using. Now, just to take a step back, if I look at the example we were just looking at, excuse me, the person that did this modeling selected a junction box as the type of panel or type of bus that he was using, even though it was labeled motor control center. This lookup table that we're talking about is included in the device library. And so if I go out here and open the library, standard lib, and again, anyone can look this up on the tools. These are in the default settings for arc flash hazards. And here under voltage, and so we're in the 200 to 1000 volt range, we're comparing motor control centers, which has both an air gap and a distance X factor entry, and selecting small junction box, you'll see that it has exactly the same ratings, air gap and distance X. So the person that did the modeling was able to make this designation without losing any accuracy as far as the calculations for distance X factor. Now, if I jump back to my presentation, one of the ways you can deal with this, because we're talking about having to set each bus with these elements, is that you can actually set the default settings for your motor control centers if you have several of the same type, or if you frequently use the same configuration, you can use motor control center designation as your default settings. So let me kind of run through this briefly. So what we're talking about is a couple things. Let's start with a new one-line diagram. And just set up my motor, ready to use my motor control center. Let's say we're going to be working on 480 volt buses. Now, if I go to the tools tab here at the top, down to equipment, and I check out or select motor control center, if I know I'm going to use several motor control centers that have all the same manufacturer, I might want to enter that data here. So let's say we're using Square D. I think it was a Model 6 that we were talking about. I really did want to capitalize it. And Model 6. And the bus rating for this particular series is 42,000 amps. Horizontal can accommodate 800 amps, and vertical can accommodate. Now again, this information I would get off the nameplate or the manufacturer's data sheet or the library. But by doing this now and setting up, this is my default setting, when I go back and build my one-line diagram and utilize the motor control centers, that information is already going to be set up for me and I don't have to worry about reusing it. Now, the other thing I wanted to point out at this juncture, and I forgot to mention we're going to be running a little bit long on this session, but when I start to do, let's say this is going to be a main lug. When I start to do descriptions of my loads, I have multiple choices. Frequently, if I do use motor control centers a lot, and if I do have some common configurations, the tool allows me to set up a library, an alternate library that I can select library loads from. So in this case, and I did this in the device library, In this case, I've set up an MCC test, referred to it as 480 volt generic. And so now when I pick out a load from that list, I can say, okay, in the 1 horsepower, and it fills in, if you scan across here, the motor specifications, the X over R calculations, the protective device that I would normally use. In this case, I'm selecting generic. And then I've designated 99 feet as I would see from the smart design, and I'd go back and update that once I got the as-builts. And then, so consequently, I can go through and populate my motor control center very easily, and do so with the knowledge that I've already considered what the ramifications are of the loadings that were taking place. Now, even if whether I'm using library load or not, the designations here can be changed. And as I mentioned earlier, we can designate a motor, a load, a VFD, sub-panels or sub-MCCs, and then we can designate loads with time current characteristic curves. For the purpose of coordination, I want to have a time current characteristic curve for that particular load. So in this case, I would designate the motor with a TCC, and I could do the same thing for a VFD, and I can also group large loads or large numbers of motors with commonality on sizes. So let's go ahead and finish a couple of these, and I'll show what the results are. Now, significance of putting in the motor control center load with the TCC. Now this I've designated even after I put in the size of the motor. If we go over to the motor specifications, we can see that we cannot put in information here. I cannot enter data once I've made that designation, and the data icon over here is flagged red. That means I have to use it to input the size or the parameters for the motor. So let's say this is a 250 horsepower motor, and X over R calculations include short circuit, and I may or may not want to include the full load current, which I'd have to do again back here thusly. Now once I've entered the MCC data, the motor characteristics, I have to do the same thing for the protective device utilizing the data dialog box, and then I would handle this just like I would a standalone breaker. And so we could either use a generic or any type of manufacturer. And again, make sure I use calculate, because this is going to be the interrupt rating that the tool uses when we take on short circuit equipment duty calculations. And then finally, because this is all self-contained, I need to enter the parameters for the cable using the data dialog, a data entry. And again, this would be just like we would handle a standalone cable. All right, real briefly, once I've done this, once I've completed all the data entry, if I try to close at this point, it's going to tell me this isn't complete. Do you want to really close it? No, I don't. What I really want to do is calculate the downstream load and create an X over R calculations for this particular load, because again, this is going to be used at the bus level for the equipment duty. And so now that I've got that, I'm ready to rock and roll as far as coordination and analysis. Not sure we're going to have time for any questions, but certainly if you've got questions you want to enter, be more than happy to respond via email. So the thing I've just done, let's come back to my slides. We talked about setting up common MCC default settings when we have multiple motor control centers, the ability to do a library load. Let me just touch on that real briefly because, again, you won't see it that often. The way I did the library load is I come back to my library, and then this can be done for panels as well, and that is create a series of loads that are pre-configured. And so what I'm looking at are motor control schedules. Here's my MCC test. Here's my 480 volt generic. So the way I envision, at least what I was planning, let's say I use square D frequently for my protective devices. I might have a 480 volt square D library load. I might also do a second one or a third one for a Cutler hammer and another one for Siemens. But here, these are essentially entered individually, just like I would if I were setting these up. And these have all the same data entered. And if there's anything that needs to be modified after I've made the entry, then that's part of my workflow to verify. I think I used 99 feet on all of these to go back and search on 99 feet loads, foot loads. Now, if I go back to my one-line diagram, and let's just kind of go to my database edit. And again, this is where I would check to see. I don't want to close it. I want to look at database browser. This is where I check to see if I'm missing any data. I'd want to look at my motors. Nothing shows up on my motor display. It's like, well, that doesn't sit well because I know I got a lot of motors in there. Well, if I come back out here, I'm in database edit. I right click in an open area and I look at options. One of the general options is include or show motor control center and panel items in database report. Now, if I apply this, I go back to my database browser and I look at motors. Now all my loads are in there and I can see where I have things completed and not completed as far as the data that's been entered. Okay, again, productivity thing, and it's not something we talk about a lot, but frankly, I think it's pretty helpful in terms of minimizing the steps that you have to do or redo whenever you're doing a study. All right, so that was configuring in the default settings, library load, and then looking at your data entry with the database browser. So now what I want to do is do a comparison of coordination on a more complicated system invoking a standalone motor control center, and then in one case we're going to outboard a single large load from that motor control center and compare it with the results we get from doing a discrete version of it. So let's go back into EasyPower. Let's close this thing and not save it. Let's close this one and not save it. And here's a system that we got. Actually, we had a number of, and if I go to the full blown, we'll see it was a much larger one-line diagram, and several of these motor control centers had some very large loads in them. And what I've done is basically isolated one out, and as a result, I'm going to isolate this other side so it doesn't get in the way. And so now here's the example of our motor control center. If we open it up, you can see that we've detailed out the main, and in each of these cases we have 2 VFD loads and 2 motors with TCC. Well, for starters, having multiple TCCs, especially if they're the same size, and they were chosen because they were both 300 horsepower motors, it's a duplication of effort. In some cases, it's more confusing. So the first recommendation I would have is to just have one motor with TCC on there, and the other isolate as a standard motor. And to do that, we'll calculate the full load current, and everything else should be good in terms of the data that was entered. And now at this point, we have a TCC, we have the motor and the breaker data, protective device, that was entered with our data entry button, and we seem to have everything kind of figured out. So let's go back to our one-line diagram and see what happens with when we go into coordination. So first of all, I guess that I don't want to call it a rush to judgment, but frequently the first thing that people do is say, okay, let's plot TCC. And this quickly points out the situation we're going to have, which is a fairly complicated one potentially, or at least frequently in the case of large motors, especially when there's multiple large motors. And if we fault this downstream bus, so the procedure is fault the most distant bus, looking at current, and what we're seeing here is the breaker in line with that large motor, and the large motor being plotted right here. So that's the starting curve. So ideally we want this breaker to be as close to the starting curve as we can get, and preferably inside of the damage curve. And then based upon where the fault is, we want that breaker to trip first. All right, so here's the maximum current that will occur in our breaker downstream for the motor. Well, the problem here exists because we can't isolate the motor. What we're faulting here is the bus upstream of the motor, and so the first breaker upstream of this bus is not the individual breaker for the motor. It's the main circuit breaker for the whole panel, the whole MCC. And so that brings us back to, if we kind of close this plot, let's go ahead and save changes. Let's not do that. We will in a second. When we're in short circuit focus, the short circuit options allow us to set either including main or excluding main. So this is a decision that needs to be made regarding the motor control center itself. If there is an arc flash barrier between the main and the main bus, then we can use including main. If there's not, then we have to exclude main, in which case we'd be dependent upon the next upstream breaker. So the point to be made is that once we get into, I can coordinate the main with the breaker above it, and that's what we're looking at when we plot the TCC, but I can't do much about coordination for this motor. I can look at it, but I can't see that it's not necessarily coordinated. But from the looks of things, we're pretty close. Now the good news is Smart PDC can accommodate it, and if we invoke Smart PDC, it does make some adjustments. In fact, it pulled out my breaker from the motor starting curve because there was some overlap. More valuable than just a pretty curve is looking at the report, and now this is what shows out some areas that really need some consideration by the engineer doing the study. And what this tells us is that there's some settings that are at the maximum that don't really give us the conventional overlap or gap in terms of there's clearance between the two breakers. Okay, so bottom line is, when we're looking at a motor control center, we really cannot tell if we've isolated the load. So the next step is to outboard that load. And the way you do that, if we go into our motor control center, let's go ahead and not save anything. Back in database edit, my motor control center, if I look at the description, now instead of a motor with a TCC, which I can include for the other 300 horsepower motor, I've outboarded this through a cable, and now my load will be determined by this particular icon, and my feeder breaker can be coordinated with the main breaker in that case. So now if I select and go into coordination and plot, I can fault that bus downstream of that first breaker, and I can make an understanding or comparison. Now I have the problem here that I've got two motors with the same starting curve, and they have the same breaker. So, I mean, a similar breaker. So now if I fault this downstream bus, I can see here now that my main current going through that breaker will be tripping at this point, and the next breaker up that it would trip would be the main breaker. And if I want to show the arcing current for this motor, if this bus were to trip, I highlight the curve for that first upstream breaker, right click, and insert the check mark. And this shows me what the arcing current will be. And we can see here, at least for arcing current, we have coordination because it'll trip my downstream breaker first, then the main breaker, and then several seconds later, it'll trip the upstream breaker that we have indicated for DP11. So this gives us the ability then to coordinate with the downstream load, and I want to compare that against the similar philosophy of doing a discrete implementation. Before I get too carried away, I do want to make another point. I emphasized the impact of the equipment duty, and here, if we kind of look at this, if I take all the buses that are set up as motor control centers, looking at the current and fault them in short circuit, you can see that we have the ability to calculate equipment duty from that particular device, from that particular display. Now, if I wanted to see what the real settings were, or the real currents actually end up being, I can either do that on a report, or I can set my threshold at some number quite a bit lower. So I want to look at anything that's within, let's say, 60% of its rating. And that gives me the ability to see if I'm close on anything. If I start to add current or loads, that would, now again, what we're talking about is the maximum current on this bus during a half cycle fault. And by setting the control system like this, when I start to go through what ifs, I can tell if I'm coming close to the ratings for at least these buses. But that's just one way to deal with that particular aspect of it. All right, back to coordination. So then from a discrete implementation, the process would be, and this again is what I would suggest starting with. Once I'm in coordination, pick out the single bus, go into current, fault that bus, and what we show in this case is the branch fault current, and because I've indicated remote current and voltage indications, if this bus faults, I'll have contributions from these other loads back through the connection point, and I'll have 7,000 amps coming from the utility and another 4,000 amps coming from these other loads. And in addition to that, this one large motor itself will contribute almost 2,000 amps. Again, this would play into equipment duty, and that's why I want to make sure that each of these buses has a rating set from the manufacturer. Now, once I'm in this configuration, I can look at my sequence of events, and the tool will indicate what the upstream tripping device is from each of these if a fault on this bus. Now this will work on these other elements, but because we're limited by which bus can be faulted, we get potentially similar results. So if this bus faults, this breaker will trip in 13 milliseconds. This breaker will trip in 90 milliseconds. This breaker will trip in 29 milliseconds, which is why we're showing a red control value. This breaker will trip in 30 seconds, and then we can go up to the fuse, which will not trip for that single bus fault. Now, if I wanted to see a report for that, under my PDC options, I'd check Create Sequence of Events Report, and then under my list of windows, I would be able to display that. Now, so the basics from that point on don't change. I want to pick out my load, the first couple of protected devices, plot the curves, look at as much as I can the current if that bus faults, and then whether or not we have coordination for each of the trip devices above it. And for some reason I was able to get closer on this particular starting curve than I did on the outboarded one. Now again, because this is faulted, these are symmetrical current values per phase for a single bus fault, and consequently they're being clipped at the maximum value that this breaker will see. These are symmetrical values and these are asymmetrical values. So BL21 we're showing here is going to see 12,378, whereas over here it's showing 13,333, and that's because it's asymmetrical current. If I right click and insert the arcing current, this will be the point that I can verify I have coordination between these devices at arcing current. Now to verify that I have time difference between them, I'll pick out two curves and use the difference calculator. And here at the maximum current, I see a separation of 12 milliseconds. If I sling it over to the arcing current, I see 23 milliseconds between the time this first device clears and this the next device will start to sense the fault. If I'm happy with that, then I take the next two devices upstream and coordinate with those. Now, I realize that, and I'm not going to save this, I realize that this doesn't answer everybody's questions. If I were to come back here and plot the same type of display here, things get much more complicated because we have these multiple loads inside, and sometimes the breakers don't always coordinate. The advantage of the tool, in fact, it's also easy to see how important Smart PDC can be in a case like this. As I invoke Smart PDC, it will give me a report of recommended settings and also the areas that are needing inspection. And so in this case, it's saying, hey, you really have an issue here where you don't have selectivity because you have something set to a maximum, and there may be a better way to handle it because of these settings. The point I'm trying to make is this doesn't answer the question for me. It just highlights that I have an issue, and it may be that I want to have try out a different breaker, different selection of breakers. So for instance, if I open up the temporary data dialog box, I can go through and say, well, what would happen if I picked out, instead of square D, I wanted to do a Cutler hammer implementation. I could go through the possibilities, and I'm just kind of picking something out, and 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 go through it what if, without a whole lot of ramifications, to see if there's a better solution to what I'm looking at. All right, so I'm starting to kind of wade off into the weeds, so I apologize for that. But I guess where I wanted to kind of leave this was, in a very complex system, at least outboarding the largest load and then not configuring or not confusing it with the other loads that may be potentially inside the motor control center is a good way to go. Not too different, and actually easier additionally, is to take a discrete implementation of the large loads and then coordinate on the way up. Ironically, the same, if I picked out this particular motor control center, invoke smart PDC, I'd get the same report back that I would get from any other configuration. And so in some regards, it expresses the value of smart PDC, if nothing else, just by giving me some recommendations of where to start. So in terms of really solving the problem, there depends on your workflow, but there could be a migration of doing just a once over analysis to see if there's any massive problems, and then take a step function of seeing if isolating the single load would help, or if it makes sense to isolate the large loads and group the rest in a discrete mode. Again, it's not one size fits all. It's essentially a tool that you can use in terms of what it takes to solve your particular problem. I would like to reiterate how useful the sequence of events is. It's available in coordination focus. It's useful when we're looking at current, not incident energy. And if we select a three-phase bolted fault and fault a single bus, then the tool makes available the sequence of events icon, and looking at the report will give us an idea of where our weaknesses lie. So in summary, I guess what we've tried to highlight is how important it is to have complete data when we're setting up motor control centers, whether they're discrete or in the form of an icon. IEEE recommends that we compare scenarios with and without large motors. In this case, they're talking about anything over 50 horsepower. For complex systems, outboarding at least the largest motor makes it easier to understand where we're having to coordinate, but in terms of being able to isolate and separate the different breakers, if you have similar loads, it may be necessary for that, in that case, to use isolated or discrete representation of the bus. In any of those cases, I would recommend using sequence of events, and then the process is to work with 2 or 3 breakers at a time and coordinate from the bottom up. Thank you for attending today. I would refer you to easypower.com. We have several tutorials that can end videos of previous webinars. There's no less than 3 or 4 webinars focusing on coordination, and you can go in and search on coordination to pull those webinars up. If you're a tool owner and have questions specific to the use of the tools, by all means, utilize tech support at easypower.com. And thank you for attending this morning. Have a good day.